Hello students, good morning and welcome to the fourth video lecture of chapter 4, moving charges and magnetism. Now in last few video lectures we were discussing about the Lorentz force acting on a charged particle moving in a uniform magnetic field, as well as we have discussed about the force acting on a current carrying wire kept in a uniform magnetic field. So the Lorentz force acting on a charged particle moving in uniform magnetic and electric field is F equal to Q into E plus V cross B. This we have already discussed. This is what we have already derived, right? This force, that is magnetic force, is Q into V cross B. The magnetic force acting on a charged particle moving in a uniform magnetic field is Fm equal to Q into V cross B. On the other hand, the electrical force acting on a charged particle moving in a uniform electric field is F equal to Q into E, right? QE. Based on this concept, we have solved few MCQs, right? As well as I think two solved example also we have discussed. For a current carrying wire, kept in uniform magnetic field, the magnetic force acting on it is given as F equal to IL cross B, and the maximum force or the magnitude of force will be BIL, Bill sin theta. You can remember like this, Bill sin theta, right? This is what we have already discussed in our last two video lectures. Now in this video lecture we are going to solve example based on this concept, two unsolved example, that is, one is exercise 4.5. Exercise 4.5. What is the magnitude of magnetic force per unit length? We want to find magnitude of magnetic force per unit length, F upon L, on a wire carrying a current of 8 ampere. Current flowing through the wire is given as 8 ampere and making an angle of 30 degree with the direction of uniform magnetic field. It is making an angle of 30 degree in the direction of uniform magnetic field with the direction of uniform magnetic field of 0.15 Tesla. Magnetic field is given as 0.15 Tesla. We want to find force per unit length. So the magnetic force acting on a current carrying wire kept in uniform magnetic field is, the formula for force is F equal to vector F equal to I vector L cross B, or magnitude of force, which you can write like F, is ILB sin theta, right? So therefore we want to find force per unit length. So take length on the other side. So F by L will be equal to BI sin theta, right? So B here is given as 0.15 I is 8 into sine 30. So 0.15 into 8 into sine 30 is 1 by 2. 2 4s are 8. 15 4s are 60 and 2 zeros are there. So 0.6 Newton per meter. Newton per meter because this is force per unit length. So answer will be 0.6 Newton per meter. Clear? Do one thing, pause this video and copy this first. Then we will discuss about exercise 4.6. Exercise 4.6. A next similar kind of example is unsolved example 4.6, or you can say exercise 4.6. A 3 centimeter wire, length of the wire is given as 3 centimeter, which is actually 0.03 meter, or if you want you can write 3 into 10 to the power minus 2 meter. Carrying a current of 10 ampere, it is carrying a current of 10 ampere. So current I is given as 10 ampere. Is placed inside the solenoid perpendicular to its axis. It is kept inside the solenoid perpendicular to its axis, means angle theta is 90 degree. Angle is 90 degree. The magnetic field inside the solenoid is given to be, the magnetic field present inside the solenoid B is given as 0.27 Tesla. The magnetic field inside the solenoid is 0.27 Tesla. What is the magnitude of force on the wire? We want to find magnitude of force acting on this wire. Now, what is solenoid? Basically, solenoid is a device which provides uniform magnetic field inside it. So you can say that inside solenoid we will always have a uniform magnetic field, and outside solenoid magnetic field is nearly zero. It is exactly similar to that of capacitor. Look, in the end of this chapter, at the end of this chapter, we are going to discuss about solenoid. We do have two topics like solenoid and toroid. So these are the two devices which provides uniform magnetic field. So solenoid is a device which provides uniform magnetic field. You might have come across this in standard 10, right? So look, in chapter 2 you have learned about capacitor. Between two parallel plates of the capacitor you will have uniform electric field. In the same way, inside solenoid we will have uniform magnetic field. So magnetic field is uniform. So the force acting on a current carrying wire kept in a uniform magnetic field, the force acting on a current carrying wire kept inside solenoid. The force acting on a current carrying wire kept inside solenoid is F equal to IL cross B. Look, you may find some confusion in this. Look, actually the magnetic force is Fm equal to Q into V cross B. This is the force, right, acting on a charged particle. And for a current carrying wire, the magnetic force is IL cross B, vector, right? IL cross B. So when to use which formula, right? So if a charged particle is in motion, for a given particle, we have to use this formula. And charged particle is in motion, so obviously velocity will be there. So this is the formula for that. But if a current carrying wire, so for wire which is carrying current, you should remember that current is I. So this formula you have to use. So F equal to IL cross B, and the magnitude of force F, which is equal to F, is ILB sine theta. So this is equal to, or F is equal to I, current is 10 ampere, length is 3 into 10 to the power minus 2, magnetic field is let me write 27 into 10 to the power minus 2 into sine 90. Now sine 90 is 1, 27 3s are 81, 81 into 10 is 810 into 10 to the power minus 4 into sine 90 is 1. So you can write this is 8.1 into 10 to the power minus 2 Newton. So the force acting on a current carrying wire kept inside the solenoid is 8.1 into 10 to the power minus 2 Newton for this given quantities. Clear? Copy this. Now, the next topic is motion in a magnetic field. Motion of a charged particle in a uniform magnetic field. Motion in magnetic field. Before discussing this topic, let us discuss something related to work which you have already learned in chapter 6 of standard 11, right? What is work? So we know that work is a scalar quantity. This is note, right? Just you have to remember. What is work? So basically work is vector F dot vector D, which can be written as Fd cos theta, where D is displacement and F is force. So on applying force to a body gets displaced, then work is defined as Fd cos theta. Now suppose if this is the body which is moving in this direction, displacement is in this direction, and you are applying force in the same direction, then in this case angle between force and displacement, in this case angle will be 0 degree. So therefore work done will be equal to Fd cos 0 is 1, so directly you can write Fd. So work done will be F into D, which is positive. But suppose if in the same case body is moving towards the right hand side, or the displacement of body is in this direction, and the force, it may be a restoring force or frictional force, any kind of force, is acting in this direction, then work done by this force will be W is equal to Fd cos 180 degree, because force and displacement are in opposite direction. So in this case theta will be equal to 180 degree, right? So cos 180 is minus 1, so this is Fd into minus 1 or minus Fd. So in this case force will be work will be negative. So if force and displacement both are in same direction, work done is positive. It means that speed of object will increase. Obviously here you can say that work is done to increase the speed, because work will provide the necessary kinetic energy. So your speed will increase, and in this case speed will decrease, right? So if you are applying force in the direction of motion, then speed will increase. If you are applying force in the opposite direction of motion, then speed will decrease. Now what happens if force and displacement are perpendicular to each other? What happens if force and displacement are perpendicular to each other? Right, this is the second case. Now let us say if object is moving in this direction, displacement is along the right hand side, and force acting on this object is in upward direction in such a way that angle between them is 90 degree. Now in this case work will be equal to Fd cos 90, and cos 90 is 0, so work done will be 0, which simply means that if force and displacement, or force and the direction of motion of a body, both are perpendicular to each other, then the work done will be 0. No work is done on it. In our case, for a charged particle moving in a uniform magnetic field, the formula for force is for a charged particle moving in uniform magnetic field, the force acting on it F equal to Q into V cross B, right? Q into V cross B. Here this force will always be perpendicular to velocity. V cross B, let us say object is moving in this direction, this is the direction of velocity, or displacement is in this direction, and cross indicates that magnetic field is perpendicular to the plane of the board and it is entering inside. So magnetic field is inside the board. So you can see that V is in this direction, right, and B is inside. So my forefinger will bend towards the board. So thumb will show the direction of force. So in this case, the force acting on this charged particle will be in upward direction. The force acting on this charged particle will be in upward direction, right? So you can say that force, velocity and magnetic field, all three are perpendicular to each other. Force, velocity and magnetic field, all three are perpendicular to each other because magnetic field is inside. This is the direction of magnetic field, perpendicular to the board and entering inside. This is the direction of velocity and this is force. So you can say that this is XYZ axis, something like that. So all three are perpendicular to each other. So it means that force and velocity, that is displacement, is perpendicular to each other. So work done will be 0. It means that magnetic field is not doing any kind of work on a charged particle which is moving inside it, perpendicular to it, right? Perpendicular to magnetic field. So work done on this charge by the magnetic field will be 0. So what actually will happen to this charge? What will be the motion of this charge? So if a charged particle is moving in a uniform magnetic field, let us say this is the uniform magnetic field which is perpendicular to the plane of the board and it is entering inside. Now remember, force and velocity are always perpendicular to each other for uniform circular motion, right? For uniform circular motion, force and velocity will always be perpendicular to each other. Let us draw and discuss this thing. Suppose if a charged particle is at this point, it is moving in this direction. So velocity is here and the force which will act on it will be towards the center or in downward direction. Suppose if we consider the charged particle somewhere over here, then its velocity will be in downward direction again and force will be in this direction. You can check. V and magnetic field is inside, so force will be towards the right hand side. Look, V, here velocity is in downward direction and magnetic field is inside the board, right? So my forefinger will bend towards the board. So thumb will show the direction of force which is towards the right hand side, right? In the same way, for this case, velocity is in this direction and magnetic field is towards the board. So my finger should bend towards the board. So force will be in downward direction. In the same way, for any other position, if you will find, force will always act towards the center of a circle, right? So it means that when a charged particle is moving in a uniform magnetic field, perpendicular to it, then it will experience a force which will be towards the center, right, of a circle, which simply means that this charged particle will perform a circular motion while moving inside a uniform magnetic field, right? So here if velocity is in this direction, force will be towards this direction. Here velocity will be in this direction, force will be towards the center. So in all these cases, force will act towards the center. So when a charged particle is moving in a uniform magnetic field perpendicular to it, it will always perform a circular motion. Hence, for a charged particle moving in uniform magnetic field, the force acting on it, uniform magnetic field perpendicular to it, actually here you should write perpendicular to B, means perpendicular to magnetic field, the force acting on it will be such that the charge will perform uniform circular motion. Look, force is perpendicular to velocity, force is perpendicular to displacement, you can say. Then in that case, its velocity will not increase and it will not decrease also. Look, if force is in the direction of velocity or displacement, velocity will increase. If force is in the opposite direction of velocity or displacement, velocity will decrease. But if it is perpendicular, then work done is 0, means its velocity will remain same. So this charged particle will move with constant velocity along a circular path if it is moving perpendicular to magnetic field. Clear? So do one thing, pause this video and copy this first. So when a charged particle is moving in a uniform magnetic field perpendicular to it, right, the force acting on it, the magnetic force acting on it will be in such a direction that it will act towards the center of a circular path, means the charged particle will start performing circular motion. The force will be in such a direction that the charged particle will start performing circular motion. So here if we consider this as uniform magnetic field which is perpendicular to the plane of the board and entering inside, right, and if a charged particle is moving in this uniform magnetic field perpendicular to it, then this charged particle will perform a circular motion inside it. The motion of that charged particle will be circular. Circular, right? Suppose if particle is here, its velocity will be in this direction and the force will be acting towards the center. In the same way, for any other point here, velocity will be in this direction and the force will be acting towards the center. So clearly we can see that the force is acting towards the center, means this magnetic force will provide the necessary centripetal force. So for that, consider a charge Q moving with velocity V in a uniform magnetic field, in a uniform magnetic field B perpendicular to it, means perpendicular to the magnetic field. It is moving in such a way that it is perpendicular to the magnetic field. Then the magnetic force acting on it will be in such a direction that the particle will perform uniform circular motion, UCM. It will start performing uniform circular motion. It will move along the circular path, you can see. The necessary centripetal force in this case is provided by the magnetic force. The necessary centripetal force in this case is provided by the centripetal force, magnetic force. So therefore magnetic force is equal to the centripetal force. Now magnetic force here is QVB sine 90. As we have discussed, VB and F all are perpendicular to each other. So QVB sine 90 is 1. So QVB will be equal to mv square by r. 1v will get cancelled out, where m is mass of charged particle, and r is radius of circular path. Here m is mass of the charged particle and r is the radius of its circular path. Clear? So you can say that this implies that mv is equal to qbr. mv is equal to qbr, or this implies that r is equal to mv over qb. This is the important relation, most important relation. R equal to mv upon qb, that is the radius of the circular path for a given charged particle, moving in uniform magnetic field the radius of its circular path, depends only on its velocity, you can say, or you can say that momentum. Means if velocity of the circular path will if velocity of the charged particle will increase, if you increase the velocity of charged particle, then its radius will also increase. This is the most important concept for another device which we are going to discuss in our next video lecture, that is cyclotron, right? One of the point for cyclotron is that with increase in the velocity, radius will also increase. Clear? So here you can see that for a given charged particle, Q is constant, uniform magnetic field B is constant, mass of that charged particle is always constant. So you can say that radius is directly proportional to velocity. If you keep mass, then radius is directly proportional to momentum, right? So if you increase momentum or velocity, the radius of its circular path will also increase. Clear? Pause this video and copy this first. So when a charged particle is moving in a uniform magnetic field perpendicular to it, it will start performing circular motion, and the necessary centripetal force is provided by the magnetic force that we have already discussed, and the radius of circular path will be R equal to mv over qb. mv over qb. Now here we know that velocity v is r omega, where, let me write r like this, r omega, where omega is angular frequency. We have already discussed about this in chapter 7 of standard 11, rotational motion. V is equal to r omega, as well as in 4th chapter also, right? So V is equal to r omega. So therefore R will be equal to m r omega over qp. So here rr will get cancelled out, which implies that omega will be equal to qb by m. This means that the angular frequency of the charged particle is independent of all the parameters. For a given charged particle, look, for a given charged particle, mass will be constant, magnetic field is constant, and charge is constant, which means that angular frequency is constant, right? Also, you know that omega is 2 pi f, where f is frequency, and this is equal to qb by m. So this implies that frequency f will be equal to qb over 2 pi m. So the frequency of the circular motion will be qb upon 2 pi m, right? Or you can say that, or periodic time t is 1 by f, which will be equal to 2 pi m by qb. That is, in this much time interval it will complete one rotation. The time required to complete one rotation will be 2 pi m by qb. Now for a given charged particle, suppose we have a proton, then mass of proton is constant, its charge is also constant, and it is moving in a uniform magnetic field which is also constant. Means this time will always be constant, right? For a given charged particle moving in a uniform magnetic field, its angular frequency, and the time period of revolution all will be constant. And this is the most important result for the working of cyclotron, right? Cyclotron will work on this principle. So it can be asked in board exam that obtain frequency of a charged particle moving in a uniform magnetic field. You can directly obtain this equation, or obtain cyclotron frequency, right? Then this equation only you have to obtain. Clear? Now what happens if a charged particle is moving in such a way that it will make some angle with the magnetic field? Look here, what we have considered, that charged particle is moving in the direction perpendicular to magnetic field. Now if the motion of the charged particle is not perpendicular to magnetic field and it is making some angle with the magnetic field, then what will happen? Let us say this is our x-axis, this is y, and this is z-axis, right? X, y, and z-axis. Let us say magnetic field is along x-axis. The magnetic field is uniform and it is along x-axis. So let us say this is the uniform magnetic field which is along x-axis. Magnetic field is along x-axis. Now we have a charged particle which is moving in such a way that it is making angle theta with magnetic field. So let us say somewhere over here, let me draw first so that, okay, somewhere over here we have a particle which is moving with velocity v, and this velocity is making angle theta with the magnetic field. So this component of velocity will be v cos theta. On the other hand, this will be the component of velocity which is v sin theta. Clear? Now v sin theta, you can see that v sin theta is perpendicular to magnetic field. Due to this velocity v sin theta, the particle will perform circular motion, right? Because it is perpendicular to magnetic field. Whenever velocity is perpendicular to magnetic field, the charged particle in a uniform magnetic field will perform circular motion. So due to v sin theta, which is perpendicular to magnetic field, this charged particle will start performing circular motion. But we do have one more component of velocity which is v cos theta. Right? This v cos theta is along the direction of magnetic field. In our textbook, they have written this as v parallel, or you can write vx, which is along x-axis. And this velocity is perpendicular to magnetic field. So you can write this as v perpendicular, or if you want, you can write v along y-axis. Right? This is v parallel and this is v perpendicular. So perpendicular component of velocity will force this charged particle to move along this circular path. But this velocity will force the particle to move along x-axis, right? Because this velocity is constant. So this charged particle should move with constant velocity along x-axis, as well as it should perform circular motion. So the motion of the charged particle inside this magnetic field will be combination of circular as well as horizontal, right? So you can say that this motion will be helical motion. Let us draw this in a proper way. Clear? Now we will get a clear idea that this charged particle will perform circular motion, as well as it will keep on moving towards the positive x direction, that is in the direction of magnetic field. So its motion will be a helical motion, just like a spring, right? Starting from this point, it will complete a circle and again it will move like this. So its motion will be a helical motion towards the magnetic field. Now the distance between these 2 points, right? Distance between 2 points, let us say P and Q, or any 2 points, this and this point, right, is known as pitch of helix. So this is pitch. Let us write this as x. So obviously, what will be the time taken to complete one revolution? This will be the time taken by the particle to complete one revolution in this uniform magnetic field. This will be its frequency, this is angular frequency, and this will be the radius of its circular path. Let me give this name. Let us name this equation 1. This is most important equation, equation number 1. This is equation 2. Let this be equation number 3, and let this be equation number 4. These are the 4 most important equations. Now, how to find the pitch of this circular path? We know that velocity is displacement upon time, or speed is distance upon time. So here, which component of velocity is responsible for this distance? This is the horizontal component, right? Parallel component, right? This charged particle will move along the direction of magnetic field due to this component of velocity. So here you can write v of x, or if you want, you can write v parallel will be equal to displacement is x over time taken is t. So pitch x will be equal to t into v parallel, where t is actually, you can write from equation 4, 2 pi m over qb into v parallel. If you want, you can simplify this further by writing 2 pi m by qb into, The parallel component of velocity is Vx, or you can write V cos theta. This will be the equation for the pitch of the circular path, helical path, right? Clear? So most important topic, obtain the equation for pitch, for radius, for frequency of a charged particle moving in a uniform magnetic field, right? This all thing can be asked. Here you should write from equation 4, or substituting value of t from equation 4. Clear? This is it for today's video lecture. Now in next video lecture we are going to discuss, of course, about cyclotron, an important device which is used to accelerate charged particle. Why acceleration of charged particle is necessary, and all those things we'll discuss in our next video lecture. As well as we are going to discuss about velocity selector, how to select a velocity, or how we can select a velocity, how you can separate the charges of a particles of different charges, right? This all thing in our next video lecture. Clear? Till then, keep on reading, keep on writing, and keep on preparing. Thank you.